everyone, thank you so much for joining today's lesson. Today we're going to be learning about the commercial applications of electrochemical cells. So here are our learning objectives. We're first going to see the simplified electrode reactions in a lithium cell, and then we're going to learn about how cells can be non-rechargeable, rechargeable, and fuel cells. We're going to learn more about fuel cells, and then the alkaline hydrogen oxygen fuel cell. And we're going to look at the benefits and risks to society associated with using these cells. So by the end, we should be able to use given electrode data to deduce the reactions occurring in non-rechargeable and rechargeable cells, deduce the EMF of a cell, and explain how the electrode reactions can be used to generate an electric current. Electrochemical cells can be used commercially. So they can be used as a commercial source of electrical energy. For example, batteries are based on the principles of electrochemical cells. A battery is just more than one cell joined together, and cells can be either non-rechargeable, rechargeable, or fuel cells. So firstly, we're going to look at non-rechargeable cells, and the first example we have is the Daniel cell, and this has an EMF of about 1.1 volts, and it's a zinc copper cell. So it was used to provide electricity for telegraphs, which sent messages by Morse code. However, soon they found out that it wasn't practical for portable devices because the electrolytes, so what the electrodes are in, are liquids, so we can't carry them about. Next, we're going to go on to this zinc carbon cell, and the positive electrode is the carbon rod, and the zinc case is the negative electrode. Now, this is when they found out that electrodes didn't need to be made out of metal, hence why this electrode was, and it acts like the inert platinum electrode in the standard hydrogen electrode. So this cell actually is the basis of most disposable batteries, so most batteries that we use only once. And also, the electrolyte is actually a paste. So this is the standard cheap non-rechargeable cell, and it has a fairly short lifespan, and it can't be recharged, so we have to dispose of it after a single use. So that's why they're very, very bad for the environment. So these are the two equations that we have set up in the cell. And we can see that the zinc is being oxidized and the ammonium ion is being reduced. So what actually happens is that the hydrogen is oxidized to water by the manganese oxide, and this prevents the buildup of pressure because hydrogen is a gas. And then the ammonia dissolves in the water of the paste. As the cell discharges, zinc is used up, and so the walls can become really thin. So these kinds of cells are prone to leakage, and this is bad because ammonium chloride is acidic, so it can be corrosive. So it can be quite dangerous if a leak does occur. But these kinds of cells are good for producing a small current intermittently, so not all the time. For example, we can use these cells in doorbells. Long-life batteries are based on the same system, but with potassium hydroxide as the electrolyte and powdered zinc instead of the manganese oxide, because it has a greater surface area and so can carry a bigger charge. And we also use a steel container so that leaks can be prevented. Now we're going to look at rechargeable batteries. So they are recharged by reversing the cell reactions. So the way we do this is we apply an external voltage which is greater than the EMF of the cell. So this forces the electrons to go the opposite way, basically. So our first example is the lead acid battery, and this is found in motors in cars, and it's basically 6 2-volt cells fixed together in series, so it creates 12 volts. And this is the equation when it's discharging. So when it's being used, this is the equation. So obviously we've already combined the two half equations. And when we're charging it, this equation is reversed. And because it's rechargeable, that does make it slightly better for the environment because we can use it more than one time. Now we're going to talk about portable batteries. So these batteries are also rechargeable, but they're portable as well, so we can bring them out with us, and they don't have to stay at home. So the first example we have is the lithium-ion battery, and this is found in laptops or phones, and this is because they are very light because lithium is quite dense. The electrolyte is a solid polymer, so that means that there'll be no leakages, so it's quite safe. And also, it can be recharged without being fully discharged. So, for example, if you're using your laptop, then you can charge it whilst you're using it. You don't have to wait for the laptop to go to 0% before you charge it. You can charge it anytime you want. And also, the battery can be bent or folded, and it still won't leak. So these two are equations that you have to know for the exam. So it's best just to memorize them. So at the negative electrode, we have the lithium plus ion being reduced to lithium. And then at the positive electrode, we have the lithium plus ion combining with the cobalt oxide and an electron to form the lithium plus cobalt oxide minus ion. However, these lithium ions can be quite dangerous because lithium is explosive with water. Lastly, we're going to discuss the alkaline hydrogen oxygen fuel cell. Now, fuel cells are used to generate an electric current, and they don't need to be electrically recharged. And so here are the two equations that we have. And these two equations you have to remember as well. So it's the lithium ion equations that you need to remember, and also this hydrogen oxygen fuel cell equations that you need to remember. So at the negative electrode, we have hydrogen added with hydroxide ions to form water and electrons. And then at the positive electrode, we have oxygen combining with water and electrons to form the hydroxide ion. And so overall, we have two hydrogens plus an oxygen to form water. And the EMF of this fuel cell is plus 1.23 volts. They don't need to be electrically recharged because they have a continuous supply of the chemicals into the cell. So now we're going to quickly run through the benefits and risks of using cells. So the benefit of using cells is that they're a portable source of electrical energy, so that means we can take it anywhere. However, the risk is that there's lots of waste, so we get lots of landfill from single-use batteries. A benefit of a non-rechargeable cell is that they're very cheap. So when you think of buying single-use AA batteries, they're very cheap to buy. However, they also contribute to waste, so lots of landfill. The benefits of using rechargeable cells are that they make less waste because we can use them more than once. They're cheaper in the long run because we can always constantly recharge them, and they have a lower environmental impact. However, there are still some kind of waste issues at the end of their lives, but obviously this will be a lot less compared to the non-rechargeable cells. And then for the hydrogen fuel cells, the benefits are that the only waste product is water, so there's no pollutants which go into the air. They don't need recharging, and also they're very, very efficient. However, the risks are that they need a constant supply of fuel, so obviously that will cost money. And then hydrogen is flammable and explosive, so that can be quite dangerous. Thirdly, is that hydrogen usually is made using fossil fuels, and also fuel cells have a very high cost. So for the exam, you'll need to remember some of these benefits and risks. So now we're going to look at some questions. So the first question asks us, the nickel metal hydride cell is a rechargeable cell. The half equations are shown below where M represents a metal. The actual electrode potential of the negative electrode and the overall EMF varies depending on the metal. For A, write an equation for the reaction taking place when the cell is being used. So when the cell is being used, the electrons are going from the negative electrode to the positive electrode. And so the only thing we need to do is combine these two half equations. But with the first equation, we need to reverse it because it's giving off the electrons, so the electrons travel to the positive. And so what we get is that first we check that the electrons are balanced already, and they are, so that's fine. We don't need to multiply by anything. So what we get is MH plus OH minus plus Ni OOH plus H2O plus the electron, and that goes to form M plus H2O plus NiOH2 plus OH minus plus the electron. And now we cancel the electrons, and actually the hydroxide ions cancel as well, so we cancel those out. And so we're left with MH plus NiOOH plus, the waters cancel as well. So this forms M plus NiOH2. And this is the equation for the reaction when the cell is being used. For B, write an equation for the reaction taking place when the cell is recharged. When the cell is being recharged, it does the opposite thing. So the opposite of this happens. So we can just reverse this reaction. So we get M plus NiOH2, and that goes to form MH plus NiOOH. And then for C, what is the main advantage of a rechargeable cell over a non-rechargeable cell? Well, that is that it can be reused more than once because you can charge it. So it's reusable. This is the rechargeable cell. Before we move on to question 2, feel free to click off the video and try it for yourself first. So it asks us about methanol fuel cells, and for A, it says write an equation for the reaction taking place when the cell is used. So when the cell is being used, the electrons are going from the more negative electrode to the positive electrode. And so the negative electrode is the half cell with the more negative standard electrode potential. And so in this case, that's this one on the right. And so this is our negative electrode. So the electrons come from here. And that means that when we combine these two half equations, we need to reverse this one on the right because it's giving off electrons. So it's reducing, it's a reducing agent. So for A, we first look at the electrons. So there's 4 here, which means that we can turn them both into 12 electrons. So we can times this equation by 2 and this equation by 3. And the other thing we need to do is reverse the second equation. So if I do that one first, then I'm least likely to forget. So I get 2 methanols plus 2 waters plus 3 oxygens plus 12 H pluses plus 12 electrons, and that goes to form, 2 carbon dioxides plus 12 H pluses plus 12 electrons, and then plus 6 waters. And now we can start to cancel stuff out. So we can cancel these H plus ions out, we can cancel the electrons out, and we can also cancel some of these waters. So you can cancel this, and this turns into a 4. And so now the overall equation is this. We have 2 methanols plus 3 oxygens, and that goes to form 2 carbon dioxides and 4 waters. And then for B, we use the formula EMF equals the standard electrode potential of the right minus the standard electrode potential of the left. And so that will equal the 1.23, because the half cell on the right will always be the more positive one. So 1.23 and minus 0.02, and that comes out to be 1.21 volts, and that's positive. Hi everyone, thank you so much for joining me for this lesson. Today we're going to be looking at harder questions for the topic of batteries. So this is a simplified cell representation of a lithium-ion cell. The reagents in the cell are absorbed onto powdered graphite that acts as a support medium which allows ions to react without a solvent, for example water. The half equation for the reaction at the positive electrode can be represented as follows. So for A, identify the element that undergoes a change in oxidation state at the positive electrode and write the oxidation states. So first I'm going to write the equation. So for A, we have Li plus COO2 plus an electron goes to form Li plus and COO2 minus. And so now we can work out all the oxidation states. So we have Li plus, which is plus 1, and then for COO2 we have minus 2, and that has to equal 0. So X equals plus 2. So we have CO as plus 2 and oxygen as minus 2. And then here we have Li is still plus 1, and then now we have COO2 minus, so that's minus 2, minus 4. So X equals plus 3. And if you can't remember how to work out the oxidation states, then quickly go back to the redox videos. So we have CO is now plus 3 and oxygen is still minus 2. And so which one has been oxidized? Well, we can see that this cobalt has been oxidized because its oxidation number has gone from plus 2 to plus 3, because oxidation can be defined as when the oxidation number increases. And so identify the element that undergoes a change in oxidation state is cobalt, and the oxidation states are plus 2 and plus 3. And then for B, write a half equation for the reaction at the negative electrode during operation of the lithium-ion cell. And so this is happening at the positive electrode. So at the negative electrode, we have this. And so because it's the negative electrode, that's reducing this. So this is what's happening at the positive electrode. So what's happening at the negative electrode must be the opposite. So electrons are given out. So we have lithium, and that goes to form lithium plus and an electron, because this electron is then going to this lithium plus and COO2 to form this ion. And then for C, suggest 2 properties of platinum that make it stable for use as an external electrical contact in a cell. It's quite useful to just remember a few properties about platinum because these kinds of questions come up quite a lot. So number 1 is that it's inert, so it doesn't react with any of the other things in the solution. And also it can conduct electricity, which is very important because we're trying to connect it up to wires and measure the EMF. And then for D, suggest one reason why water is not used as a solvent in this cell. Water actually reacts with lithium and it forms lithium hydroxide, and that's the reason why. Lithium hydroxide. Before I move on to question 2, feel free to click off the video and try it for yourself first. So this question is about the alkaline hydrogen oxygen fuel cells. And so for A, use the table to calculate the EMF of the alkaline hydrogen oxygen fuel cell. So what we do is we use the equation EMF equals standard electric potential of the right minus the standard electric potential of the left. And so the 2 equations that we need are this one and also this one, because these are both working in alkaline conditions. And what we do now is we think which one is being reduced and which one is being oxidized. Well, one thing to note is that this table is actually not the electrochemical series because they've written it the other way around. And so it's very important to spot that the most negative is actually on the bottom, because that can trip you up. So this means that this is going to reduce this. And so the bottom equation is the one which is giving away the electrons. And so that means that the bottom equation is the cell that we put on the left, and the right equation will be the one on the top. And so this gives us an EMF of 0.4 minus 0.83, and that equals plus 1.23 volts. So for B, write a cell representation. So we've already kind of thought this through. We know which ones are on the right and which ones on the left, but now we need to figure out which of the species in those half cells will be going in the middle and the outsides. So the rule is that the most oxidized ones are in the middle, so the ones which have bigger oxidation numbers. And so let's first work on the left half cell. So this is where this equation comes in. So we have to have this hydroxide and this hydrogen. Some people like to include the water as well, but it's okay to miss it out as well. So now we think which one has the higher oxidation number. So OH minus and H2, and it's for hydrogen. So the oxidation number for H2 for hydrogen is 0 because it's an element. And then for this one, it would be plus 1 because the oxygen would be minus 2. And then the hydrogen will be plus 1, and that equals the overall charge, which is minus 1. So hydrogen is plus 1, and that means that the OH minus goes in the middle. And because the OH minus and the H2 are not solids, that means we need to use a solid, so we use platinum. So platinum always goes on the outside as convention. And then we use a solid line because we're changing phases now. And then we have the H2, which is a gas, and then another solid line, the OH minus, which is aqueous. And now we have the salt bridge, which is the two double lines. And now we work on the other equation. So now we need to have the oxygen and the OH minus. And so again, we work out the oxidation states. So we have O2 and OH minus for oxygen. So for oxygen, the oxidation state in O2 is 0 because it's an element, and in here it's minus 2. And so that means that the oxygen goes in the middle because it's got a higher oxidation state. So we have oxygen, the gas, separated by a straight line, and then the OH minus ion, which is aqueous. And then again, we need something solid, so we use platinum. So platinum goes on the outside. And this is the cell representation. Then for C, construct an overall equation that occurs when it operates. So when it operates, that means that the electrons are going like normal, so from the more negative electrode to the more positive electrode. And so that means that the electrons are coming from this bottom equation. So that means that this bottom equation needs to be reversed before we combine the half equations. One thing to spot is that the electrons are different. So we've got 2 electrons here, but 4 here, which means that we need to multiply this equation by 2 so that we can cancel out the electrons at the end. And so we have 4OH minus plus 2H2 plus O2 plus 2 H2O plus 4 electrons, and this goes to form 4 waters plus 4 electrons plus 4 hydroxide ions. And now we can cancel stuff out. So we can cancel this hydroxide ion out, and we can cancel these electrons out, and we can also cancel these 2 waters out and turn this into a 2. And so the overall equation that we have is 2 hydrogens plus an oxygen goes to form 2 waters. And then for D, give one reason other than cost why the platinum electrodes are made by coating a porous ceramic material with platinum rather than by using platinum rods. And that's because the surface area is increased greatly, so it happens a lot quicker. So increase the surface area, so we have faster reactions. And then for E, other than its lack of pollution, state briefly the main advantage of a fuel cell over a rechargeable cell when used in an electric motor that propels a vehicle. The main advantage is that we don't have to stop it to be recharged because it has that continuous flow of hydrogen and oxygen. So we have a continuous flow of hydrogen and oxygen. So as long as there's a continuous flow of hydrogen and oxygen, that means that the electric motor will be able to propel the vehicle. And then for F, hydrogen-oxygen fuel cells are sometimes regarded as a carbon-neutral energy source. Give one reason why this may not be true. And the reason why is that if we are to have a continuous flow of hydrogen and oxygen, where they come from is from the burning of fossil fuels. So this is not good for the environment, and it's not carbon neutral. So the answer is burning of fossil fuels to produce hydrogen and oxygen is not carbon neutral.